CPU, GPU. Here is about, for this image, you see the graph card use 170. We use about 773 milliseconds. If you use a GPU, just take 33. For this image, about 39, 58, 12. We use a GPU. Yeah, for that one. So one of the students tests a lot. So we got about 50 or 150 images from the database. We compare all the different methods, but those are not published. So those are the images. I use a graph card. I use segment. So here I think we don't do manual input. But if you want to do manual input, mostly you can single out just one object. Single out one object. Also here you can see a little run, and then you just put a curve. If you put a green curve here, and this will jump to outside to be correct. Yes?
I have two questions about the computations.
Yeah.
So usually you use the single precision for computing or double precision?
MATLAB is always double precision. C code, I think, just a single precision. Yeah.
GPU also used the
single precision. Yeah. So
maybe the lower architecture is maybe possible in GPU.
Yeah, so here we also did GPU. In fact, the GPU we did here is a very lazy GPU. So essentially, the new MATLAB, there's a new function. You can write your code in MATLAB and compile it. And after compiling, you can run that MATLAB on GPU. So that's what we did here. So essentially, that's what we did here. Is like this GPU. So this GPU, we don't write our own GPU code. So essentially, we wrote the code in C and use MATLAB to compile it, and then you can compile into a CUDA executable GPU implementation. So this is a new MATLAB function. It's not perfect, but still you get acceleration, and this is very good, very good. So essentially, you just have a C code, and then you can run it in MATLAB. You can also run it on GPU. But even you run this on GPU, you get quite some accelerations. And this code is all public, so you can get it. I will tell you where you get it in the end. So this, you see, this code we have in C. You can run it in C, in MATLAB, in GPU, in 2D and 3D. But still, the code is very elementary. If you want to use it for real application, you need to expand it quite a lot.
Can you specify the GPU machine you use?
That depends on the amount of a compiler. So we didn't write the GPU code. So essentially, we write a C code, compile in MATLAB. MATLAB produce a GPU executable. It's not the best, but still quite good.
But it may be more accelerated in the native GPU code.
Right,
yeah.
Right. Even
MATLAB has much of the memory copy in the GPU machine that delays very long rather than the computation time. So.
Right. Yeah, here we did it for 3D. So this is a 3D quadratic segmentation. Quite big in size. Yes. So here 150. This is 2028 second. So I think this mostly is GPU. Is done in GPU. Here even 4D ultrasound. You try to get. See 4D, and then that will be. Also, it's about 0.1 second. This might be too optimized. Yeah. So here is like a brain segmentation 3D. So therefore, what related to one of the questions, if you want to use it for tracking, so which means you have something moving in one of the frames that you want to track around. So you can either do it as a 3D segmentation, or you do a 2D segmentation, and then how do you interaction? We haven't done that. But right, because mostly, you see, I think those things is not the mathematician should do. I think those things we should leave it to the people who works with real applications. Oh, sorry. So as a mathematician, you see, we just designed the methodology and then found what's the best method or how to improve the method. So there we can see that this is another way to get global minimizer. So that's the reason you see on the first page of of the slides I list quite a number of technologies. We start with a level set, phase constant level set, and then each of those ones present is a new way to solve it. Level set is very good, very flexible. But those all the new method essentially you can solve the same problem, produce same result as a level set, but you get other more and more advantage, faster, stable, global minimizer. Yeah. So in terms of global minimization, so now we have been talking about two ones. So one is relax, this one to interval. Yeah. So this is one, and the other one is just using max floor. Another one just use a graph card. So graph card always guarantees. Graph card approach always guarantee minimization, and then we have just been talking about the max floor, continuous max floor. So this you will get. Also a convex problem. You solve it, and then you get a global minimization. So now we continue from here. Especially, I think it's very interesting to observe the Lagrangian for the flow conservation. That's essentially the cut. That's really something interesting, very interesting. So it's just Lagrangian for the flow conservation that turns out to be the cut. Originally, we explained the cut. This is all the bottlenecks, Now we are coming to multiphase. You see, here is two-phase. Here is a two-phase, here is a two-phase. We talk about something multi-phase. So now we especially, in fact, this is very special. This is very special multi-phase. We are talking about even multi-phase. We are talking about three multi-phase approaches. So this is one of them. So the two-phase. So two-phase. So this is a two-phase mean cut. So you have a cut. Here F1, F2, assume C1, C2 are known. Here it depends how do you approximate the length. Here is a mean cut for two-phase case. And then if you want to do the four phase, if you use a level set, you need to use the two level set functions. If I don't use a level set, if I use just two binary functions, phi1, phi2, two binary functions, and then the continuous model is so the level set representation is phi1, phi2 are two level sets. And then you get alpha heavy set phi1, alpha heavy set phi2. Here you get you see all the characteristics things phi1, 1 minus h phi2, maybe u0 minus c1 square. So these C1s we purposely put here. We purposely first we put C2 here, C1 here, C4 here, C3 here. I was explaining to you why we purposely do, instead of using just C1 here, C2 here, C3 here, C4 here, we purposely, there is a reason. So we will soon come to that one. And then this is original transverse. So 1 minus h is phi2, and then you just do the four things. Instead of using level set, so we can just use a binary function. So essentially phi1, phi2 take a 0 or 1. Use a binary function, and then you take a heavy set. You see everywhere you take heavy set away. And then that will be, so you use a binary function to solve the transverse set. That's essentially what is written here. So we call this the binary level set method. So you use a binary function phi1, phi2, 0, 1, Here is a data term. Data term is given here, and here is an approximation of those two total variations. Total variation phi 1, total variation phi 2. So here is an approximation total variation. It depends. So here is a neighborhood. Here is a neighborhood. It depends. If you only use 4 neighbors, so this will be the anisotropic TV. If you use more neighborhood, Cauchy-Crofton, and then you approximate the length. So here is an approximation, the total variation of those two terms. And this is, you see, like phi 1, phi 2. So here is one of the constant, another constant. So this will be the 4-phase transversal. And now we are trying to use a graph card to solve this problem. We are trying to use a graph card to solve this problem. So here, those things will come later. We are talking about the submodulars. So the first thing is that how do you construct a graph to solve this problem? The multiphase transversal problem. And the graph we construct, in fact, is in this way. This graph seems to be new. We have not seen it in the literature. And so how do you construct graph to solve the transversal? Essentially, you have one pixel. And then you copy this pixel. And then make a link from source to this one, and make a link source to this one, and make links to here to here. This is one pixel. If you have 2 pixels, you have a PQ, and then you copy both of them. And then you see you add the link, this is 2 pixels. So this connection, the original connection between those pixels is also copied to here. This will be 2 directions. If you have 3 pixels, how it looks like. So you just add 1. If you have only 2D image, so essentially you copy this image once. Each one is connected to source sink. So this is a graph we call the transversal graph, CV graph. This is a very special graph. So we haven't seen in the literature people has been constructing such a graph. You copy each pixel once. If it's 1D, you copy it just into one line. If it's 2D, you just copy the whole plane to here. And then each of them you connect to. And the original connection between the pixels, you keep the original ones. And this is a graph we are constructing. So those edges will be used for data fidelity. Those edges will be used for regularization. These are edges. Especially, so here is this graph, how it works. And this graph, so if those 2 edges are cut, and then we see this pixel belong to class 1. If those 2 edges are cut, we see this belong to class 2. If those 3 edges are cut, we see belong to class 3. This should be arrowed to here. Those 3 edges are cut, belong to class 4. So in this way, you see that if the cut should be separate the vertices into 2 groups, one to the source, another to the sink. So the cut must be one of those 4 options. Must be one of the 4 options. So this graph we call it the CV graph. If you want to segment any of the pixels into 4 classes, and the cut through each pixel must be one of those 4. It's very difficult to draw it now, especially for 2D. If a 2D, yeah. So here is my 2D image. You copy it once. You copy it once to here. And then you have all the pixels here, So this pixel should be connected, and then you connect it to T. You also connect both to S. And then if there is a cut, so must cut this one with one of those 4 options. Now we call this graph the CV graph. And so therefore, so you need so here is the thing we try to minimize. So here for this graph, you must assign cost as your A, B, C, D, E, F. You must assign capacity to each of the edges. So we see that when you cut this one, we say class 1, so therefore the cost of this cut should equal to this one. So the cost of that cut is A plus B. Is A plus B. So it should satisfy this one. And then the cost of this one, if we say this is a cost of a cut of this one, so we assign to this one. And then the cost of AED, so that was AED, this should equal to this one. And the cost of CFB, and this should equal to this one. So therefore, if your cut should minimize the time wasted, you must assign the ABCD to satisfy those relations. Even C1, C2, C4 are known. C1, C2, C4 are known. So you need to assign the capacity in such a way. Right. Assuming you see C1, C2, C4 are known. So this is you have four equations. You have 6 unknowns. You have 6 unknowns. So it's over determinate. It's a redundant system. If you do a little bit study, you found out you can always guarantee A, B, C, D. You can always guarantee A, B, C, D are positive. But you cannot guarantee E and P are positive. So there are some cases it could happen, you see E and P both are negative or one of them are negative. There is no positive solution. There is no positive solution. And in fact, we checked it out. If these EP are positive, it implies this condition must be correct. And this turns out to require the graph is submodulars. The graph is submodulars. So if we should have EP and FP should be positive, it turns out this is a condition. That's also the reason you see why we put so here. You see here we don't put C1, C2, C4. Instead we do a special order. That was due to the condition. You see here is a C2, C3. Here C1, C4. Purposely we do it in such a way. And this condition turns out this condition is correct if the 4 constants are evenly distributed. So which means the distance between them are nearly the same. That condition is correct. If 2 of them are, so here 2 of them close, 2 of them close is correct. This is also okay, but this is not okay. So this means you see you have a lot of intensity are very close, one of the intensity are far away, and then that condition will be violated. And this is a very difficult situation, which means that those contrast, there is very little contrast with 3 classes compared with the other class. So mostly in such a case, you should segment into 2 classes instead of into 4 classes. But in those cases, that condition will be correct. And that you can guarantee EPFP is positive. EPFP is positive. And so there, we call this one is we call this one is especially CV graph. Is especially constructed for the CV model. You do 4 phases. So there are infinite many solutions for A, B, C, D, E for each pixel. We can guarantee A, B, C, D are positive. If one of them is negative, or if both are negative, and then we have a trouble, right? And then if a trouble, so it's not the end of the story. We still have something to get rid of it. Especially here is why we choose if C1, C2, C3, C4 in 1 pixel, this is the order of the 4 constants. You must take F1 equal to C2, F2 equal to C3, F3 equal to C1, F4 equal to. You must take such a thing. If you don't take such a thing, if you just take a wrong, you see instead of here you put the C2, which is the second largest, you put the last one, and then this condition mostly you cannot guarantee. Mostly you cannot guarantee this is correct. So therefore, even there is this trick, you need to do this trick to guarantee to make the method work. Yeah. And so also if one of them is negative, and then we have another way to solve it, because in a graph, if the capacity is negative, in fact negative graph still makes sense, but not for general graphs. So therefore there is one way to modify that. If this is negative, we simply take that away. So we take away this one and then increase this one, and then guarantee that's a positive. If one of them is negative, so we simply take it away and then construct another graph, and then we do several iterations. There's one way to get rid of it, to get around of this one. So this is to use a special graph. We have also tested. So essentially, we also use a graphical method to solve it. So you construct such a graph, assign the capacity, and there's I think I didn't write it down. There is an X-ray formula to get the A, B, C, D, E, F. So we don't solve that system. We just have a fixed formula to solve all those numbers. So therefore, you don't need to compute. We just use one fixed formula, assign the capacity. If one of these is negative, we just take that edge away and do in another one, and then you see, check out the residue and do something more. So this is one way to do it for multiphase. Here is the input image. D is A, B, C, D. So here, this is our methods. So yeah. Here is input image. Here is output image. So there's no human interaction here. I can't remember how many phases this is. This is mostly like one, the wet one, black one, green one. I think this is like it's a 4-phase, because the time vector is especially for 4-phase. Here is we try to check. You see how many pixels the E and P are less than 0. Essentially, there is no point less than 0. But for some other images, you get negative E and P's, and then we need to play a trick. Here we have a power beta. Beta you can either take 1 or take 2. So take 2. Take a 2 is I think take a 2 is better, or 1 is better. I can't remember. There's some modularity. So that condition is yeah. So that's this is one of the ways to get multiphase. So that's 4 phases. So if you want to get 8 phases, how do you do? So you copy once, you get 4 phases. If you look at level set method, if you get 2 level set, you get 4 phases. 3 level set, 8 phases, and 4 level set, 16 phases. So therefore, essentially, you can extend this one also to 8 phases or 16 phases. But then that's becoming quite complicated. There's another multiphase approach. This multiphase, I think I'm not going to talk about it. This multiphase approach, this is essentially where you do that. You want to segment. Here is a 2D image. You want to segment into n phases. So when you do that, you copy n this image into n pieces. And then you connect each pixel, each point to the source, and connect to each point to T. And then the connection between the pixel is the same. And then you put the same amount of flow into each of the pieces. And then due to the capacity, you assign the capacity here F1, F2. I think here F1, F2, Fn. The capacity, you have a capacity differs in this part. You put the same amount of flow, and then depends, you see the flow which is coming back to here, you determine which class your pixel should belong to. So this is another way to do the multiphase. Yeah. I think the code I'm going to give you later is essentially based on this approach. It's also very, very fast. Very, very fast. So this is another way to do multi-phase. If you don't copy, if you just do one phases, mostly you get two phases. If you copy, you can do n phases. So here is now we come to the layered graph. So like this layered graph, so if you want to do multi-phase, so you copy, so the previous one, so here you copy and then you push side by side. And here is a layered graph is you copy, but then the flow goes from bottom to up, or from up from right. So this is a layered graph. Layered graph. Here C1, C2, C0, C1, C2, and then you push up, and then depends on which edge is cutted, and then you determine a class for the pixels. In fact, this idea, if you tell the secret, this idea is very, very easy, right? So I think here is essentially where the idea really comes from. So assuming you see here, I have my omega. It could be 1D or 2D or 3D. So here is my omega. I want to separate it into omega 1, omega 2, omega 1, omega 4. So if you want to segment this region into 4 classes, and then you need 4 labels. So here, label 1, label 2, label 1, label 2, label 3. So therefore, you see that if you want to segment this one into 4 classes, you need 4 labels. But however, you see at the levels I did, you increase the dimension by 1. So I don't segment over here. So I increase the dimension by 1. And then I segment in this region, right? And then you just 2 labels is enough, right? So here u equal to 0, here u equal to 1. So therefore, you see that on your original dimension is a multi-phase problem. But if you increase the dimension by 1, it becomes a 2-phase problem. I think this is essentially the secret here. Right, because originally, if you segment here, you need 4 labels. But I copy this one, increase dimension by 1, and then you just need you see 1 label is enough. So I think this is the secret of idea. Also, if you read if you read the several approaches recent in the literature, they call the lifting technique or the calibration technique. So that was essentially related to this one. It's just there's a mathematical techniques. So in a low dimension, you need to in a low dimension problem, you need to multiple labels. You increase the dimension by 1, and then you just need 1 label. That's enough. So that's a secrecy. That's a secrecy, and that's essentially this layered graph is trying to do. So you increase dimension by 1. You essentially copy the graph several times, and then you do this one, so you get the label. You get the label. Get multiple labels. Yeah. So here is mathematically how do we? So here is the vertices. You have an original vertex, but you copy it n-1 times. So here originally you copy n-1 time. Here is the edges. So the edge 1 is those edges. So here is edge 1, and here edge L is the edge between the layers. Edge n is to the sink. So those are. So here is edge n. Here is edge 1. Here is the edge between the layers. So here is mathematically define all the edges. Here is a regularization edge is the edge between the pixels. So you have a natural between the. So here is the regularization edge. Here is essentially you assign the first layer is minus C1, the second layer C2, C3, the last layer Cn. Here is the cost between the points. If you do this one, so you remember, you cut the first one, you get 1, cut the second, get a 2, cut the third one, you get 3, cut the first. So this is, you see, every such a cut, you have a corresponding indicator function. And then you can show that the cost of a cut is exactly equal to this one plus, I think here is wrong, here is not the characteristic, here is a total variation of 5. Because you see that here you see the function jump from 1 to 2, here is to 3. So here is a label jump to 1 to 3. And then you're cutting this edge twice. So essentially you see 3 minus 2, there is a 2. So therefore it's not the length, but it's the length times the jump. So therefore the cost there is no phi here. So if a phi is this label, so this kind of regularization is regularized the total variation of phi instead of a characteristic function. So there is a typo here. So you can see that on this layered graph, there is no battery. So on this layered graph, so essentially you are minimizing this one, which is instead of the length of the regions, the total variation of this phi. So the jumps come into the minimization. Oh, yeah. As I said, you see that for such a thing, you see this is also cut. Right? If this is a cut, and for this label, you label 2, label 3, you get label 4. You see 1 pixel, you get multiple labels. And then we can prove that you see for Manfusha, such a kind of illegal cut cannot happen. If this is a cut, you just connect to here, and then you can see that cut is have a smaller cost. So therefore illegal cut cannot be minimum cut. So you will always get a unique label. You will also always get a unique label. This needs some kind of proof. Also numerically, as you did, mostly it works. Yeah. So the last thing I want to talk is so here is a CV graph. So this graph is especially for CV. As we did for the two-phase case, we can also make it continuous. So that's multiphase max 4 for the CV. And so therefore, yeah, it works. Yeah, it works now. And then it doesn't work. So here is, you see, we do the CV using a binary function instead of a level set function. We call these binary level set methods. So here is the total variation. Here are the 4 terms. So we have explained what's the reason is why we put the C2, C1, C4. That's the reason why we put it here. Because if you don't put this one, and then you need to have a different ordering for the. Instead of, you see, we can also, we have a graph card for this one. Also, we try to make it continuous. What's a continuous marked flow for this model? And then the continuous, essentially, you have this image and then you copy it once. And then you connect each of them. And now you have one plane, you copy once. And so therefore, there is to source, there are 2. This is from the first plane, and this is from the second plane. So this will be the flow. And then here are the constants. I think here should be all bigger than 0. So here are C, P1, P2, PT. T is to the think, P2. And here, and then you see you have 2 planes. Each plane has its own flow within the interface. So here even P1, 2. No, there is even one more flow. There is a flow between the two planes. You have one plane here, if another plane. So here is a flow between the 2 planes. I think the negative one just maybe is in the another direction. Positive. And then you have a flow, 2 conservation flows. Here is a flow between the 2. Here is a 2 conservation of the flow. So there's a conservation of flow on plane 1, there's a conservation of flow on flow 2. This will be the continuous max flow for this special. So that's what discretized. If you make a continuous one, so here will be the continuous max flow. Here is a continuous max flow. And this is something very interesting. So if you do this one, and then still you use 2 Lagrangians to eliminate the flow conservation. And you have lambda 1, lambda 2. Yeah. For the flow conservation, where is the P1, P2? Oh, here is the PS1, PS2. And the flow conservation, there has been a lot of rearrangement. You have 2 flow conservations. I use Lagrangian. You use Lagrangian. So you try to conserve those 2 flows. So you multiply by this lambda 1, this multiply by lambda 2. You do a lot of rearrangement. So you see lambda 1, some lambda 1 jump to here, some lambda. So this is, if you don't have this one, that's a max flow. Right, you do a lot of rearrangement, and here is still the flow constraint. It's very sketchy, so we are not going into the detail. If you eliminate, for this case again, if you eliminate all the PS1, PS2, PT1, PT2, only reduce it to lambda 1, lambda 2, and this is what we get. This is what we get. It's very complicated. And then here is you only have a lambda 1, lambda 2. And so here the ABCD, you solve it from such a system. Assuming here you take either 1 or either 2. And this is something very interesting, because if you look here, this doesn't, you see, this doesn't look like this one. So this is the original Tanvay. So this is the original Tanvay, right? So this is the 4-phase. Here is you see here you can relax. If you're directly working on the original multiphase Tanvay, this is a problem. So you can relax this one to the interval, right? But this functional is not convex, right? So therefore you see you do global minimization, there are 2 things. One is convexify this one. But even you convexify this one, you see like a phi 1 plus multiply phi 2 is not convex. Even here you get negative, so those are not convex. So therefore, that's the reason people become very surprised. They see that I claim I can get a global minimization for the 2-phase Tanvay. How can you do it? Because even you convexify here is not convex. How do you guarantee? How do you convexify the problem? This is people. I think a lot of people have been trying. Once the 2-phase are finished, a lot of people have been trying to convexify multiphase. And the crucial thing here. So even you can, the constraints you can convexify, the functional is not convex. So how do you convexify? How do you convexify? In fact, due to, you see, through all this whole process, we come up to here. You come up to this problem. In fact, for this problem, it's quite complicated. It's quite complicated. If lambda 1, lambda 2 equal to 0, 1, in fact, this functional exactly equal to the previous one. So in case you see that if lambda I equal to 0 or 1, and then this functional, you see the functional will minimize here. It's very complicated. It's equal to this one. Equal to this one. So therefore, over this side is equal. But however, you see that this is non-convex, and this one is a convex. This one is a convex with the lambda, assuming E and F are positive. So that's a secret. That's a secret. So therefore, you see that for this functional, so for this functional is not convex. But however, when you assume phi 1, phi 2 are binary, 0, 1, so there are infinitely many ways to write this one. You see that if phi 1, phi 2 is binary, you see that phi 1 square equal to phi 1 cubic also equal to phi, right? So which means you can replace this one by the square of this function. You replace it by cubic. So that's one way to rewrite it. But there are infinite many other ways. So the trick is to pick one of them, which is convex. So this is one step further for convexification for nonlinear, non-convex models. Especially here, if you want to minimize a binary variable. You convexify interval, and here, assuming they are binary, you have an infinite many ways to write this one. And pick one of them that is convex. I think there must exist many ones that are convex. You just pick one of the ones which is a convex. So I don't know if I make the idea clear. I think this point is very crucial. So you not only convex the constants, you also get a convex. You also convexify your energy function, which is normally non-convex. So mathematically, any function you can convexify it. You give an arbitrary function, you can always find a convex function. Especially, you see, like in 2D. So therefore, you see, you give an arbitrary function, and here is a 0, here is a 1. I just need to find another convex function which goes through those 2 points. So definitely there are infinite many of them. All right. So you just pick one of them which is very good for you. And that's what we did here. So we just pick this one. So this one equal to the original convex functional when lambda 1 lambda equal to 2. However, this function is convex. So essentially, mathematically, maybe I'm trying to emphasize too much of this one. So mathematically, so originally, so we have a function. So here is a 0, 1, here is a 1. So this functional is not convex, right? But then we get another function which is a convex passing through those 2. And then you see you have originally just minimize over those 2 points. Now I minimize over this interval. And then the problem, you see that your global minimizer is here. The best way is you see that your global minimizer of the new function coincides with your original function. But for this case, it does. But maybe for many other cases, it doesn't. But this is a crucial idea. I think I should open up a lot of new research activities for many other computer vision problems. Because most of the computer vision image processor models, they are nonlinear, non-convex. So that means local minimum is always a problem. Initial value dependence is always a problem. So this idea should be one way. I don't think that you can do all of them. But if your model has a very good physical background, mostly you should be able to do it. So that's the thing we want to emphasize. So in convex, so this new model exactly equivalent to the convex model. And so it will be convex if EF are bigger than 0. And for this model, in fact, we can prove thresholding optimal lambda 1, lambda 2, which threshold means that you put a value lower than this value threshold to 1, lower than this threshold to 0, above the threshold 1. Threshold lambda 1 will give a binary global solution to the original convex. So that was essentially at this figure. So you see that the global minimizer, if I threshold it, it must be the global minimizer for the original problem. And that we can prove for this convex model. But I think here is we just do a very simple case. The two-phase case, that's easy because the convex energy is already convex. The four-phase case is not convex. So this is really a new idea. There's a new idea. So I think this one is as a mathematician, especially as an applied mathematician, who are working with PDEs, who are working with minimization. So this could be really a point. But we shouldn't try this one on every model. But for reasonable models, so this will give a very good. You see, like a convex, we can prove. You see, lambda 1, lambda 2 if we really solve this, the dual problem, and that will give a global minimizer for the original problem, right? So you see, like in the two-phase case, so it was, you see, we do it, and the graph card, there's several things we have done it. Moreover, we want to emphasize, so the global minimizer of the max flow convex CV is a global minimizer of the original non-convex CV model. So if you just see this result, people don't believe it. They say, I don't believe, how can you do it? But then if you tell them the idea, so you see, people start to realize. Even it's non-convex, and we can get it's a global minimizer, right? And the global minimizer is a guaranteed binary. So just threshold we can prove must be, so they're not true for many other approaches. Not true for many other approaches. So this is the last thing I want to talk about global minimization. So global minimization, so essentially we have talked about this one, and the last one you see that it's just not only convexify the constraints, also convexify the functional. So there are infinitely many ways to write down the functional if the minimization is a variable. But you should not only convexify the constant, but also convexify the functional. So this is one more element to the whole thing. Right. And still you see that the people don't believe. They know, you see, that if you don't have a fidelity term, if you just minimize the length of the interface problem, this is proven in the literature. This is the NP hard. This is the NP hard. So therefore, people still don't believe. You see that if you just throw away the other things, you can do global minimizer. In fact, so that's really come to the point that the Chang-Vessel model sometimes is not minimize the length of the interface. Sometimes the lengths have a double counting. So therefore, Chang-Vessel model cannot produce. So essentially, what I'm saying that so the total variation of phi 1, which is a binary variable, and the total variation of phi 2, in some cases, this is not equal to the length of the interface. In some cases. Do you catch me? Yeah, in some cases, this does not equal to the length of the interface. And that's the reason we can get global minimizer, no threshold, no approximation. But if you really exactly, instead of regularize, maybe I show you when it does not equal to the So assuming you see phi 1 is bigger than 0 here, phi 2 is less, and then you have a phi 2, you see like phi 2 is bigger than 0 here. So therefore, you see the length of phi 1 total variation equal to this one, and then the length of phi total variation equal to this one. So therefore, you can see those two lengths are counted once, but this length is counted twice. So therefore, this one does not equal to this one. So in some cases, and other cases, you are minimizing the length of an interface. For this case, you are not minimizing the length. So here you have a double counting. And that's the reason, you see, we can get global minimizer. If you really want to minimize exactly this length instead of this one, and then we need to add some more constraints. If you do this one, and then you will be minimize the length of the interface exactly. But if you do this one, and then we cannot guarantee. Then threshold solution is not guaranteed to be exactly global minima anymore. So therefore, here we utilize some very intrinsic property of the model. If you want to minimize the exact length, and then threshold is not guaranteed to be exactly global minimizer. You just approximate the global minimizer, but not. Very often, even that approximation is a very good one. Is a very good one. Mm-hmm. Yeah. So this is one more point to be emphasized. One more point to be emphasized. Yeah, so here you see that all the global minimizations, we need to assume Ci is known and the minimization with omega I is global minimized. But I think yesterday who was asking, you see, if Ci is also unknown, if I want to minimize both of them, can you get global minimization? So answer is yes. So here, this approach is essentially, they call it parametric max flow. So therefore, you have a max flow problem. This max flow depends on parameter. So those Ci are the parameter. And the parametric max flow, and for very special structure parametric max flow, you see that the flow pattern only have a several turning point on the Ci values. And then you can pick one of the Ci value which is max the total flow, and that's also okay. So that's what they did. Here is they are using lifting. So lifting is a very related. Here we even use another approach. So those are three approaches. So you can convexify the problem when both Ci and omega, when both of them are unknown. And then the computing cost is higher. So it's not as quickly as the one we have seen. So it take a little bit longer time. Especially you see this one is very expensive. This one very expensive. So this one is relatively cheap, but still more expensive. There's another thing you see that even you don't know, and so therefore here is here. So what we have been talking now, we can convexify if only omega I is unknown. So therefore now you see both omega I is unknown, Ci is unknown, Ni is unknown. All of them are unknown. Can you convexify or not? So that you can also convexify it. So this means if you can do this one, the only input is alpha and the input image. How many phases? It is determined by the minimization. What kind of constant you get on each phase is determined by minimization. Where are the boundaries? This is determined. So this you can also convexify. But we have tried on this on real data. For some real data, this is really very good. But some other real data, you see, if you specify n, that has a lot of help. It makes the problem better. If you don't tell how many n, if you just use this alpha to control the n, sometimes you get the n which is not very good for real applications. So therefore, really give n as a specific number. If you know the application, if you know the n, so that helps. I think you see there are other works which is trying to determine the n. Even I think Kim was talking, so she was also talking about determining n. So maybe I should add your work sometime later. So that was you don't fix the n, but let the code to determine automatically. Yeah. Here, so I'm trying to point to related papers about this convex relaxation, and especially for continuous max flow, Gilbert's flow was the first one to notice. This one is in the two-phase case. Is just they just convexify the constraints, and recently is using convexify the characteristics. So here is a number of people have been doing. You see here also they have been convexifying the constraints using the split Bergen. Here this paper uses a lifting technique to convexify. The things I'm talking mostly is published in those several papers. We have a number of recent papers. But one thing I want to emphasize is that you see those new methods are really, because it's a convexify, it's a global minimizer, so it really doesn't depend on initial value, always converted to the same solution. Another way is that due to all those new techniques, the speed is getting much faster. It's really quick now, really quick. So I really encourage, so if you should try segmentation, many people still feel so comfortable with the traditional methods. But if you really try this one and compare with, in fact, with the traditional methods, we are solving the same problem. The minimizer, we are solving exactly the same model, same problem. So the solution should be the same. But you just get the solution much faster. Here is a code. So I think this is multiphase, this is two-phase, that's a two-phase that he was running. So you can get all those code, you can have a try. So in there, we have a MATLAB implementation, we have a C implementation, we have a GPU. So the GPU is a lazy GPU. So you compile it in MATLAB and then run GPU. I think you can easily convert those code to 3D. You can easily convert it to color images. Yeah. So once you convert to color image, and you can do textures, as Miyun was talking about. If you use a Gaussian transformation, so essentially that's a vector data. If you do color image and you can do texture, you do a lot of other things. So our contribution here is just we try to develop a set of fast algorithms, very stable global minimization. But you see the way to use them for more application, there, I think there's a lot of more potentials. Also, you see, we don't develop a new model. You see, all the models are exactly the same model. The Chang-Vesey is a Manfoshan, but how do you solve it? So the way we solve it, the numerical methods we solve it are new and fast. So the contribution is on the numerical part, Yeah. Okay, I think stop here. Any question?